discussing some of the work that we're doing at JCAP towards bringing components and material assemblies into solar field prototypes. This work spans efforts that are related to materials discovery, interface engineering, and integration. And I'll kind of pick up where Matt McDowell left off in the previous talk. As he described, JCAP and actually the broader solar fuels community over the last 4 or 5 years has really made significant progress in the stabilization of unstable semiconductor materials. And really at this stage, it's possible to say that we can protect most of the main types of semiconductors that one would conceive of using in this type of technology. This includes group 4, 3, 5, 2, 6 semiconductor materials, metal oxides as well. As Matt showed, you can apply these types of approaches to both planar, nanotextured, and mesoscale assemblies, and both polycrystalline thin films as well as bulk single crystalline semiconductors have now been protected. However, one of the defining features of JCAP is to move beyond some of the basic science research advancements, which we do pursue, but to also translate these advancements into functional assemblies that can be evaluated in testbed prototypes, ideally for overall water splitting in spontaneous water splitting devices. So with that in mind, what I'll talk about today is, this was referred to actually by Harry Atwater earlier, as 2 of the parallel approaches that we pursue within JCAP. One being the stabilization of otherwise unstable photoelectrodes, and I'll talk a bit more about how that can be applied to overall water splitting devices beyond what Matt just spoke about. And second, how we can drive towards intrinsically stable semiconductor systems through the understanding of some of our best existing semiconductors to guide the discovery of new materials that will be intrinsically stable and not require advanced approaches to thin film corrosion protection. Okay, so I'll begin by talking about atomic layer deposition for stabilization, in this case of photocathode-based, photocathode illuminated devices. So the goals of JCAP can be pretty succinctly stated here in terms of the prototyping efforts. We want to achieve greater than 10% solar hydrogen conversion efficiency in an overall water splitting device with a demonstrated stability of at least 24 hours with a stretch goal of 100 hours for initial demonstration purposes. A really important requirement that isn't necessarily broadly adhered to in the broader community is that we really need pure product streams, particularly of the fuel stream, but there's 2 specific reasons for this. The first is that we need to ensure that we have and generate safe devices, so we do not want to create explosive mixtures of oxygen and hydrogen. But also, if you consider end-use applications for the hydrogen, you'd like to reduce the amount of gas cleanup that's required following the generation of the solar fuel. And finally, we want to create these devices at a reasonable scale for which we can test the function of the devices and identify the major failure mechanisms. So we specify this to be at least a scale of 1 by 1 square centimeter. The engine of these prototype or testbed prototype devices is shown here. They're based on triple junction photovoltaic cells, on top of which there's an anti-reflective coating, and contacts are applied to the surface where the electrons are extracted at intervals, spacing intervals that allow for most efficient charge extraction with minimized shading or light absorption by those contact materials. On top of these systems, we apply an ALD layer of approximately 100 nanometers thickness in order to physically protect the substrate, as Matt described in the previous talk. And then we pattern a hydrogen evolution catalyst onto the surface. So we make then a stack of electrode protection layer and in localized regions, hydrogen evolution catalyst. So we localize where the product is generated. There's a couple of advantages to this patterned approach. The first is, of course, our catalysts can often be strongly light absorbing or opaque, so this minimizes parasitic light absorption. It also has the side benefit of localizing where we generate product and where bubbles are formed off of the surfaces of the materials, and this bubble handling is actually somewhat of an issue in these higher efficiency devices that are really vigorously generating product. On the top left here, you see the results of a functional test of one of these materials. So as a function of time, this is showing the photocurrent density and corresponding solar to hydrogen conversion efficiency. We see we have an efficiency of about 12% for this particular device, and it's stable for about 6 hours. However, what you do see is after that period of 6 hours, an eventual decline of that efficiency. If you optically inspect the the device after this test, you see that there are a few discrete failure points on the surface. These actually occur at these contact catalyst stack systems that I was describing before, and you see that because these are not self-passivating materials, that there is a kind of catastrophic failure of the material. It's bulk etching, and this will propagate until the material is actually no longer present, except as corrosion product in solution. What's important, though, is to understand how these materials are specifically failing so that we can overcome these failure mechanisms. To do this, here is shown a focused ion beam cross-section that we have then imaged with scanning and electron microscopy at the location of one of these electrical contact catalyst stacks. And you see right off the bat that this is a relatively complex structure, and there are multiple potential failure points on such a system. It has a complex high surface area microstructure. There's many different materials with the opportunity for differential thermal expansion that could lead to the origin of strains, particularly under light-dark cycling where there are temperature variations. There's highly concave regions that could be considered geometric stress concentrators, and of course, as there's multiple process steps and multiple tools that are required to make one of these systems, there can be residual process stress that eventually leads to crack formation. If we look at one of these failure points in a similar fib cross-section, the bottom left was shown the as-grown system, and the bottom right is where one of these systems has failed. We see that indeed cracks do fail. These propagate through the system along interfaces. Eventually these interfaces fail, the material delaminates. This allows for physical interaction between the electrolyte and the underlying chemically sensitive semiconductor substrate, and that initiates this catastrophic corrosion failure. However, by recognizing these modes of failure, this imaging is just one portion of that. We also do a wide range of spectroscopies to see what's chemically occurring. But by identifying failure, we can then begin to overcome it. And so here's an example. I can't describe exactly what the approach is, the approach modification, but we are able to modify through our understanding our strategy to corrosion protection, and in this case we have achieved an efficiency above 10% for approximately 40 hours at this 1 square centimeter scale, and importantly, while incorporating product separation into this material. So this is producing pure hydrogen and pure oxygen product streams. I'd just like to show a brief video of one of these in operation. I think it's always fun to see bubbles. What you'll see here is, I'll use the mouse to kind of illustrate this. This is the photoactive device. On the right and left, there's membrane inserts. So this is where the ions, through which the ions can conduct, but the products are not able to cross over from the analyte to the catholyte chamber. It's a cathode up device, so what you will see is hydrogen bubbles coming off of the surface, and it may be faint from out there, but there are thin vertical lines, and these are the patterned catalyst layers that are on the surface. So this is the sample in room illumination, lab illumination. The image will go bright white. That's when the solar simulator is turned on, and the camera readjusts to the new light levels, and then you should see the device under functional conditions. So there's the solar simulator coming on, and here's the bubbles coming off. And this is a real-time video of this occurring, and I think this highlights how the pattern catalysts also help with handling of bubbles. You see that the bubbles are localized to where they're being generated, and that aids them to come off of the surface in ways that do not reduce the solid electrolyte contact area or lead to too many lensing effects that could reduce the overall light impingement on the semiconductor. Okay, so that's a brief summary of one of the various prototype devices that we have within JCAP that's based on stabilization of otherwise unstable semiconductors. In the second part of this talk, I'm going to take a step back to some of the more basic science advancements that are really based on the discovery of intrinsically stable semiconductor materials. The previous devices are rather expensive semiconductor stacks. They allow us to deepen our understanding of functional assemblies, but the ideal case would be to have semiconductors that are naturally stable. Bismuth Vanadate is a material that's quite commonly investigated in JCAP as well as the broader solar fuels community. Because it has a moderate band gap, it's a strongly light-absorbing semiconductor material. Its band gap is a little too big, and its stability is not perfect. However, it's a great starting point as a material that can provide a very large photovoltage and does absorb visible light. In fact, it has been integrated together with amorphous silicon photovoltaics by the Van der Kolk group at Helmholtz Center in Berlin, and they have achieved a close to 5% solar to hydrogen conversion efficiency with an integrated assembly. However, the material does suffer from poor electron hole separation. It does have a tendency to photocorrode, and there is a deep need for understanding of the basic electronic structure of the material, the dynamics of photocarriers, and the role of defects on recombination and efficiency in the system. By understanding these features of the material, we hope to guide discovery and development of the next generation of materials with reduced band gaps and opportunities for higher conversion efficiencies. As a starting point for this work, we sought to directly determine the electronic structure of the material through a coupled theoretical and experimental study in which we computed, as shown on the top left, the partial densities of states near the band edges within the material, and we were able to directly probe these using a range of synchrotron X-ray spectroscopies, both absorption and emission. And by comparing experiment and theory, we were able to develop a comprehensive model for the electronic structure of this material. And most importantly, we were able to test some of our theoretic models to see what they were getting right and where they were lacking. And what was found is actually there was a substantial underestimation of the Bismuth 6s oxygen 2p coupling in this material system. These are exactly the states that form the valence band where photogenerated holes are located, and this is absolutely critical to the function of the material. So through having this experimental data, our colleagues in theory were able to refine their models, and through this refinement, we're then able to go one step further and predict a new composition of matter, which in this case was bismuth antimony vanadate, which they predicted should have a narrower band gap than pure phase bismuth vanadate because of the higher line antimony 5s level compared to the bismuth 6s level. A number of researchers within JCAP attempted to synthesize this using bulk and thin film synthesis methods. It turned out to be rather difficult to obtain this in a pure phase form. However, our colleague in JCAP, Raffaele Buonsanti, using powerful colloidal nanoparticle synthesis methods, was able to synthesize this rather complicated material with compositions up to 20% antimony in the bismuth antimony vanadate. This is an initial stage finding, so the efficiencies that you get from a brand new material are not going to be directly competitive typically with materials that have been under development for decades. However, she was able to show that the band gap was reduced by a few hundred millivolts from this 2.5 value to about 2.3, which is great in terms of going the right direction towards having a material that can capture a larger fraction of the solar spectrum. And these reductions of the band gap corresponded ultimately to increases of the photoconversion efficiency. Another thing that was identified through the fundamental studies of the electronic structure of bismuth vanadate was the strong localization of electronic states in the conduction band of the material. This was observed directly through these combined theory and experiment studies, as well as by other researchers who've observed this through functional testing of the material. Also, I'd point out that Buddy Mullins's group at UT Austin has recently identified polaronic transport within the materials, considerably contributing to the poor electron mobilities. So all of this points to a need to overcome poor electronic transport within this metal oxide semiconductor. One approach that's been pursued in the past is doping of the material. Within JCAP, we've now developed those scalable methods of doped bismuth vanadate synthesis based on reactive co-sputtering. This is a complicated process, but it's highly reproducible and repeatable. And in fact, we were able to obtain very high photoconversion or photocurrent densities with an optimum doping concentration of about 3.4% molybdenum in the films. We can do this over 10 by 10 square centimeters, and the functionality of the material is very homogeneous across those 10 by 10 square centimeters, as well as between different batches. And so here on the bottom right is shown photocurrent density as a function of applied electrochemical potential for 5 independent deposition runs where we see highly reproducible characteristics. So this is kind of the traditional approach to overcoming transport limitations, but we also want to explore new concepts of how we might overcome poor electronic transport in some of these defective and potentially polaron conducting metal oxide thin films. And for this, we again turn to the colloidal nanoparticle synthesis approach in order to make heterostructured nanocomposite materials of dual phases. So in this case, we mixed bismuth vanadate nanoparticles together with secondary oxide phases that have improved electron transport properties relative to the bismuth vanadate. So here's shown the example of how this works. So bismuth vanadate in this case was mixed together with tungsten oxide at the nanoscale, but with controllable length scales of their interactions, and as a reference with alumina, where we would expect no charge injection. So in the ideal case, what we should have is photoexcited electrons from bismuth vanadate are transferred rapidly to the tungsten oxide. This physical separation of electron and hole should increase the efficiency of the material and improve charge extraction. On the bottom left is shown transient absorption spectra. This is a pump probe spectroscopy where we can directly probe these types of electron transfers. The magnitude of the signal, without going into too many details here, in this spectral range can be considered proportional to the electron concentration within the bismuth vanadate. We see when we have pure bismuth vanadate or bismuth vanadate with alumina, the character is very similar. However, when we introduce the tungsten oxide at different length scales, we can get electron extraction into this secondary phase. If we look at much longer time scales, we can see what happens to the holes that are still in the bismuth vanadate. So now we're looking in a different spectral range. Again, the signal is now sensitive to the presence of holes within the bismuth vanadate. And at this time, we now have to look out to time scales that range out to seconds. Because of this large physical separation between the electron and hole, we can get long-lived photoexcited holes within the bismuth vanadate that allow us to reduce recombination within the material. This translates directly into improved performance. We see an approximate doubling of the saturation photocurrent density within these materials. And we believe that this kind of concept can be broadly applied to metal oxide thin film semiconductors in order to overcome some of the intrinsic transport limitations that often plague these materials. So that brings me to the end. I hope I've convinced you that pursuing two parallel approaches is valuable. We're able to make rapid progress through the stabilization of otherwise unstable photoelectrodes using semiconductors where there's a broad knowledge base. However, moving forward, we would like to have materials that are intrinsically stable so we don't have to rely on techniques like atomic layer deposition for their protection. And in order to do this, we take the best existing materials, understand them deeply, and use that knowledge to guide the discovery of new compositions of matter. And finally, I'd like to thank, there's many colleagues who have contributed to the work that I presented here today, as well as the Department of Energy for funding of JCUP as a hub. And it's important also to point out that we work very closely with our colleagues at the National User Facilities, Advanced Light Source, Molecular Foundry, NSEM, and I should have the NERSC label on here as well.
What was adjusted in the electronic structure models to bring, for bismuth vanadate, to bring it better in line with the experiment?
It was actually the Bismuth 6S level, so I'm not a theorist, but it was off by about 3.
Bismuth what?
The Bismuth 6S level. Yeah, it was off.
But how did you fix it?
So I would defer to Lin Wang, who's the computationalist who did that work. I'm not qualified to answer that.
Right over here.
Yeah. Can you just flip back the last one slide, voltammogram, the one before? Yeah.
Yes.
Can you explain why you don't see the classic S-shaped plateau? You see the increase in the current almost linear. Is that a Onic?
Yeah, we're still investigating that. I mean, traditionally, if you see that in, say, a pure phase material, it would be that there's a mismatch between the transport length and absorption length. And so you're increasing the width of the depletion region, meaning that you're extracting more and more of those charges out of the thin film. In this particular case, as a heterostructured nanocomposite, I don't want to immediately say that it's exactly the same effect that you're observing because there's additional complexities there. But it would, I would suspect, have something to do with more efficient extraction of carriers by increasing regions of space charge.
Right over here.
You showed this movie, very nice movie with a high evolution. What is the open circuit potential of that device, and what catalyst do you use for the oxygen evolution?
Okay, so the device itself generates approximately 2 volts of photovoltage in this triple junction stack. I'd note that could be tuned. People know a lot about these systems. You can, on a computer, design the device and get the photovoltages and photocurrents that you would expect. This is the case that we were using here. As for the catalyst, This was operated under 1 molar sulfuric acid. I believe it was a mesh, and have to say it was with iridium oxide coated on that mesh.
This is a follow-up question. So what is the current of that video?
So that was a device. I won't say it's exactly the same device, but it's a current density. It's in the exact same class of this device that is at between 9 and 10 milliamps per square centimeter, which corresponds closely to approximately 12.
Also, do you have idea about hydrogen production rates in terms of area?
So we have measured the hydrogen production rate, and it corresponds to close to 100% Faradaic efficiency for this device. This failure is not generating a substantial fraction of hydrogen or other product until really those cracks propagate to the point that you have a material interaction with the electrolyte. And so during this window of stability, it's at a very high Faradaic efficiency that corresponds.
11.3%.
Sorry?
Efficiency 11.3%.
For the video one, I think our highest one does exceed 12%. There's some details about how you mount the material, nucleation of the bubbles, if you have, and actually displacement of the bubbles from the surface. If they begin to accumulate, this will reduce the efficiencies.
Okay, so turn it back to Adam. So let's think.
Okay, so we'll take a 5-minute break before we start the third session of the E2S, which will be 2 talks on hydrogen technologies. So 5 minutes.